Okay, guys, let's get started. So, my first question is: does anybody have a winter jacket I can borrow? It's absolutely freezing in here. Okay, so we have a homework due on Friday, just to remind you. On the syllabus, we had this policy that says that if you have like a conference or, 3 problem sets due in the same day or something that's foreseeable but it's going to give you some kind of trouble, then you should email us 5 days ahead of time and we can give you an extension. Because it's the first homework and I assume a lot of you didn't read the syllabus, we'll just make a special exception. So if you have something like a conference deadline or something of that nature, maybe, for some reason multiple problem sets all coinciding on this Friday, you can still email us today and tomorrow and ask for an extension, and we'll give you a 2-day extension. In the future, for these kind of foreseeable things, we ask that you give us 5 days, and then we'll grant you an extension. 5 days notice. Of course, for true emergencies, we can always grant you an extension, but I was just talking about kind of foreseeable things. Okay. I don't think I have any more announcements than that. So I wasn't here on Monday, but I think Siva probably did a great job. He covered all the way up through, I was told, conic programs, and then he just introduced what a conic program was, and that was all. So we only have a couple more things to say here. I guess part of the punchline of this lecture maybe didn't get delivered because you haven't seen yet like all of the hierarchy, essentially. So a conic problem is the most general kind of optimization problem that we've introduced at least in this lecture. And it's of this form: minimize C transpose x subject to some linear constraint on x, and some other linear function of x being in a cone. Okay, so this D is like, if x is a vector, just think about D as a matrix. Okay, in that case, if x is a vector, so this just says dx plus this little d is in a cone. And this cone actually also has to be convex, and we learned what a convex cone was a couple lectures ago, right? It's convex, and it has the property that you can scale its elements arbitrarily by positive numbers, and it stays in the set. And this actually happens to be a really, really general problem form. It contains LPs. Okay, we can see that immediately because we can just, let's say, take x to be d to be the identity, and this d, little d to be 0, and take k to be the positive orthant, then this says that x has to be bigger than or equal to 0 in every component. The positive orthant is a convex cone, and that's the standard form LP. It also contains SDPs for a very similar reason. Just take this k to be the positive semi-definite cone and interpret x in this problem as a matrix now. Okay, so this x could be a vector or a matrix in this problem. So it contains LPs and SDPs. In fact, it's so general that a solver like CVX, which you're using on homework 1, and I assume for a lot of people it'll be a useful tool to know how to use, it tries to cast everything that you tell it into a conic program. And then it applies very general algorithms for solving conic programs. They're mostly based on interior point methods, which we'll cover later in the course. It's not necessarily fast to do so, to cast, let's say, an LP into a conic program and use an interior point method, or to cast whatever you pass as CVX. But it's a very general strategy, which is why CVX can be so successful at solving all sorts of problems. So that should just give you an idea that conic programs are actually really, really broad, and they encompass, pretty much everything that you'd want to solve. Convex problems outside of conic programs are more exotic. So a very special type of a conic program is called a second-order cone program. So you'll see in a minute why we're introducing this as a kind of a special case. But an SOCP, or second-order cone program, is one in which this cone K has a very particular form. So we still have a linear objective, we have linear equality constraints, but we have inequality constraints of this form. Okay, the L2 norm of some linear function of our variable is less than or equal to another linear function of our variable. So you should, bells should go off in your head and say this is a convex constraint. You can see that because the L2 norm is convex. I'm composing it with an affine transformation, so this is still convex. And this is actually both convex and concave. I can subtract this linear function to the other side, and negative the linear function is still convex. So this I can rewrite this as one whole convex function less than or equal to 0. So this is a convex problem. In fact, this SOCP, this is the general form for an SOCP, is a cone program. And to see that, we're going to actually just remember that the second order cone was defined as follows. It's the set of all pairs x comma t, where x is a vector, t is real valued, such that the L2 norm of x is less than or equal to t. Okay, and therefore we can actually cast this inequality, right? Some L2 norm of some affine transformation of x being less than or equal to some other affine transformation of x as this pair, right? di times x plus little di, comma ei transpose x plus fi being in a second order cone. Just saying exactly by definition, the L2 norm of this is less than or equal to this. Okay, so now if I consider this alone is a conic constraint. It's a linear function of x that we're saying must be lying in a cone, a second order cone. And you can think about it by how do I get kind of all of these into a single conic constraint. If I stack all of these, right? Let's say I stack all of these into one big vector. So I think about, like stacking the rows of di, for example, stacking di, the entries of di into one big vector, etc. I can write that as just some affine function of x being in a Cartesian product of cones. So a Cartesian product of sets, in case you've forgotten, it's a fancy name. It's a very simple concept. A Cartesian product B is just the set of all AB such that A is in A and B is in B. Okay, so I just get all pairs of elements, one being in the first set, the second block being in the second set. So if I were to say, for example, D1 x plus D1, comma E1 transpose x plus F1 being in Q1, and the same thing, but with 2's being in Q2, right? Then I can think of this as just some linear function of this form being in the Cartesian product of sets. Okay? I mean, I guess this may be a confusing way to write it, but I think hopefully you know what I mean. I mean, maybe I'll just write it like this so I don't confuse you too much. I mean a vector, let's say, whose entries are as follows. So I'm going to just list the entries in the order that they appear in the vector. So I have a vector like this, and I'm saying this is in a Cartesian product of cones. So this first block is in Q1, and this second block is in Q2. That's what that means. So I can write all of these SOCP constraints as just one big affine transformation of my variables being in a cone, and the cone is just a product, Cartesian product of second order cones. Okay, so an SOCP is a SDP. I'm sorry, I haven't told you that yet. An SOCP is a conic program. That's what we've shown here. Okay, and I just, Freudian slip, I just told you the result of the next slide. Well, I guess first we'll get out of the way that every LP is actually a second order cone program. So that's not hard to see. Because I can just, for example, take a special case, let's say in which this di matrix was 0, this di vector was 0, and I'm actually just comparing every entry of x to 0. Right, I can just, for example, choose this ei to be the ith standard basis vector, this fi to be 0, and if I collect these constraints, it says that x is bigger than or equal to 0. That's the standard form LP. So I can get an LP out of this. And what I just kind of mentioned was that every second order cone program, we just proved it was a conic program, but in fact it's an SDP. So it's actually in an even smaller class than conic programs. It's an SDP. And this is a very important thing to know, because this is actually going to kind of complete the hierarchy for us. Currently, if I gave you a homework problem that said, prove that every QP is an SDP, and I didn't give you any hints, it would be kind of a difficult thing to do. But we're going to actually get at it by looking at this particular inclusion. SOCPs are SDPs. Okay, and then I'm going to prove for you in a slide that every QP is an SOCP. So we've introduced SOCPs basically as a tool to go from QPs to SDPs. Right, we're going to prove that they lie right in the middle. So let's do the right-hand side of that containment. So every SOCP is an SDP. So the way to see that is really just, we want to write, let's say, what's unfamiliar if we're thinking about SDPs are these kind of inequality constraints, but we're going to want to write that in terms of some kind of positive definite constraint. And we can do that by just recognizing that the condition that the norm of x, the Elton norm of x, is less than or equal to t, it's actually equivalent to a particular semi-definite constraint involving t and x. And this is true, well, this is true for multiple reasons, but one way to realize this is true is to invoke what's called the Schur complement theorem. So if I give you a block matrix of this form, okay, and I ask you, let's say, to check whether it's positive semi-definite, it turns out that's actually equivalent to checking that the following matrix is positive semi-definite. This is called the Schur complement of this matrix. So I take A minus B C inverse B transpose. If that's PSD, and actually if C, let's say, is itself positive definite, then we know that this thing is positive semi-definite. So let's use that. Let's apply that fact actually to this particular matrix, this particular choice of block matrix. So by the Schur complement theorem, this being PSD, so look, the T here, let's say, is positive. So this piece is definitely positive definite. It's just a vector. I mean, so it's just a real number. So saying that it's positive definite reduces to just saying that it's positive. And we're going to take T to be, let's say, positive. This being positive semi-definite by the Schur complement theorem is equivalent to A minus B C inverse B transpose being positive semi-definite. So A minus B C inverse is just divide by T, because it's a real, times this thing, which is B transpose, being PSD. Okay, this is this matrix being PSD, but that's actually the same as just saying this is true. Okay, I can multiply through by T. T is positive. And if we just were to check what this means, say just by the definition of positive semi-definiteness, we would see immediately that this is the same as the L2 norm. Let's say the squared L2 norm is less than or equal to T squared, or the L2 norm is less than or equal to T. Okay, so that's the proof of this equivalence that I gave you up here. And now you should think about our variable as, let's say, being something involving x and t. And so we've written these constraints as positive semi-definite constraints. And if we had linear transformations, that doesn't really matter. We could always somehow, by adding more equality constraints, just write these of the form, let's say, norm of y being less than or equal to something like s, and then add some equality constraints to say this must be equal to y, this must be equal to s. So that just adds to these equality constraints. And then we just rewrite these constraints via this relationship as PSD constraints. Okay, so proving that we get an SDP out. Oh, question, yeah. This one? This one. Various ways. So you could, for example, so this means that if I take A transpose T squared I minus X transpose A is bigger than or equal to 0 for all A. So I could, for example, take I could take A to be equal to X, actually, and that would give the result. If I took A to be equal to X, then I get T squared times the norm squared of X minus, I'm going to get actually the norm to the fourth bigger than or equal to 0. Yeah, that's one way to see it. You could also maybe look at the lowest eigenvalue. It's another way to see it. Any other questions?
Step from the matrix to the T minus matrix to
this? So this came from the Schur complement. It's just a particularly kind of simple version of this fact here. Okay? Okay, so currently, maybe the picture is something like this. We have LPs. We have QPs. Okay? Then in a separate world, you have LPs. You have SOCPs. And you have SDPs. Okay, we've proved all these containments so far. Right, it's quite easy to see that, let's say, an LP is an SOCP. This proof we just did right now, and it's quite easy to see an LP as a QP. Okay, and we also proved that actually SCPs are conic programs. So there's an even bigger bubble here, which is conic. But I don't know where QP fits in here yet. Okay, that's what we haven't done yet. And QPs actually fit right in here. That's what we're going to prove. That QPs are an SOCP. And then once I do that, we have the hierarchy. So this is just another kind of fact you have to recognize, that if I take a QP, let's say QP member is C transpose X plus quadratic in X, so usually write it as 1/2 X transpose QX. I can rewrite a QP by introducing a slack variable T. Okay, so replacing the quadratic part by a T and actually bounding, let's say X transpose QX, 1/2 that by T as a constraint. That's just introducing a slack variable. It's a trick that we had talked about a couple lectures ago. Okay, so this is the same as having a quadratic and no constraint here. And okay, we did this because this is linear in our optimization variable, which is X comma T. No? This is also linear in our optimization variable. Okay, now we want to prove that that this constraint we can actually write as a second order cone constraint. So this one we already can. Right? I already explained why LPs were SOCPs. We can always write linear constraints in terms of second order cone constraints. We don't know how to write so far this as a norm of something involving X and T being less than or equal to something in X and T that's linear. Okay, we don't know how to do that yet. And this is just kind of another fact that you know, that it's maybe seems a bit tricky to know where to come up with this, but this is the equivalence. That a quadratic being less than or equal to T is the same as a particular norm of a linear function of my variable X and T is less than or equal to another linear function. So we're going to just prove that by just expanding. Bless you. So if I say that this is less than or equal to 1/2 1 plus T, all right, I can also square both sides. And this thing, if I square, think about this as, you know, being a vector transpose itself. So I get this thing transpose itself, which is exactly 1/2 X transpose QX. This Q to the half is sometimes called the symmetric square root of Q. For any PSD matrix, it exists. It actually comes directly from the eigendecomposition. It satisfies this property. It's symmetric, and Q to 1/2 times Q to 1/2 is Q. Okay, so if we have a PSD matrix, we can always do this. This thing transposes itself. Well, this is just a real number, so I get 1/4 times 1 minus 2t plus t squared. And this thing is going to be 1/4 1 plus 2t plus t squared. Okay, and I can just cancel out these common terms. And if I move the minus 2t times 1/4 to this side, I'm going to get a half t plus a half t. So this is the same as 1/2 x transpose qx less than or equal to t, as we needed it to be. Okay, so this now is of the desired form. It's the norm of some affine or some linear function or affine function of our variable being less than or equal to some affine function of our variable. So what we did pictorially, just to go back to this picture, is we've put QPs right here. Right? We've just proved that QPs are SOCPs, and then that completes the hierarchy. Okay. Did Siva give you any non-rigorous personal opinions about these programs yet? I usually do that when I give that lecture. No, he didn't? Okay. I didn't know if he would. I suggested he could, but I'm not sure if he was comfortable. So I drew these pictures in a particular way in the slides for a reason, and that there is quite a big gap. So this is, again, my opinion. This is nothing particularly rigorous, between QPs and SDPs. And it's unclear to me really how much bigger conic programs are than SDPs. That's less intuitive. But I can tell you informally, the way I see it is that SDPs are a lot bigger of a class than QPs. And these are kind of easy problems to solve. Easy algorithmically. And the moment you go to an SDP, you're kind of in trouble. So the dirty secret of convex optimization, in my opinion, is that we think, we teach SDPs as if somehow it's like everything's convex, life is good, but an SDP with 1,000 variables, let's say that has dense linear equality constraints, is actually not an easy thing to solve. So only very special SDPs can we solve efficiently. Generic SDPs are very hard to solve. So that's why I drew this picture this way. So you want to avoid SDPs. If you can formulate your problem as an SDP, it better be a fairly simple one, or it better be one that has a fairly nice structure, basically, or it better not be very big. Because if it's a big SDP that's kind of generically dense in terms of the, let's say, the equality constraints, then that's a very hard thing for solvers to handle. A question, yeah?
So do SOCPs fall into there, or is that not necessary to reduce problems to that form?
So you mean my non-rigorous opinion again? Yeah, I think of SOCPs as actually kind of close to SDPs. So they're pretty hard. I mean, there are nice SOCPs and nice SDPs. Like, for example, the graphical lasso is an example of a very... Oops. I just turned it off. Sorry about that. Oh, that's convenient. Okay, we're back up. So the graphical lasso is a very nice SDP. It's very easy to solve compared to typical SDPs. There are others, like, for example, trace norm minimization is fairly nice. We'll actually see how to... Trace norm imputation is even actually fairly nice. So we'll see how to do matrix completion with proximal gradient in a few lectures. So there are some nice SDPs that we can solve that are big. But, they're kind of more, in my mind, special cases. Whereas, I mean, right now, given all the work that's been done on optimization, QPs are, unless they're absolutely enormous, they're not really going to give you a problem computationally. Okay. And another kind of course, completely non-rigorous, kind of hand-wavy perspective is that I'll convey is that, we're really talking about something like this. So we're talking about things in some kind of small dot there. But there are a lot of useful problems, obviously. I mean, that's why we have a whole course on it. So, okay. So let's jump into gradient descent. I'm actually going to make a statement about non-convex problems in this lecture, so we'll be able to see we can say some things even beyond convex problems. And I'll try to do that periodically throughout the course. Although, of course, our focus will be, as we've always said, on convex stuff. So I'll skip the review because we just did all that. So let's just go right into gradient descent. This is our first lecture on an algorithm. We just left the kind of first theory unit that we did, where we just kind of got our grounding in terms of all the concepts that we need. And now we're entering our first algorithms unit, which is on first-order methods. So these are methods that really just use first-order information, meaning the gradient. So we're not going to talk about second-order methods until a little later in the course. So as a simple place to start, we're going to start with gradient descent. But we'll see already there's a lot of interesting things to say about gradient descent. I know it's a very simple algorithm. You guys probably all know it, but there's a lot of interesting things we can say. And we'll just kind of get more sophisticated from here as we go through the first-order methods unit. So let's just think about unconstrained, smooth, convex optimization. So this function has a derivative. That's what we're going to assume, and it's convex. It has full domain. If this wasn't true, then really some things would have to change that are not that important. So we'll just keep it, thinking about full domain for simplicity. And we're going to, as usual, denote the optimal value by f star and a solution by x star. So here I'm assuming, as I'm going to be throughout the course without kind of any warning, that a solution exists. We talked about the fact that, convex problems could actually be minimized out at infinity somewhere. We say that the solutions don't exist in that case. But we're going to assume that we're not in that case. Okay, we're going to assume that a solution exists. And gradient descent, which I assume you guys have all seen before, it's a very simple algorithm. It just says choose some initial point, x0. Okay, compute the gradient of my criterion function at x0. And move, let's say k is 1. So take x0, move it in the direction of the negative gradient by some positive amount tk, or t0. Or I guess t1 if k is 1. Okay, so we're going to be moving it in the direction of the negative gradient, and we're going to call it x1, and then we'll repeat. Continue to compute the gradient, move in the direction of the negative gradient. So the gradient is essentially pointing us downhill, right? It's pointing us in a direction that we think that the function is, along which the function is decreasing, so that's why we're doing this. The negative gradient is doing that, pointing us downhill. Okay, and we'll just say stop at some point. We'll talk about more precise ways to stop a bit in this lecture, and then more when we talk about duality. But you stop at some point. So here's a couple pictures of gradient descent. You've already seen these, in fact, but now you know it's gradient descent I was showing. I was just showing these in earlier lectures. So here's a convex function in 2 dimensions. So I have, let's say, x1, x2, and the mesh is supposed to be displaying the values of the criterion. Okay, so it's like a bird's eye view of the criterion. And I'm running gradient descent. The minimum is somewhere in here of my function. And kind of see that visually. I'm running gradient descent from various starting points. Those are all these points. And I'm denoting the path of iterates. Okay, it's discrete, but I chose a really small step size, so it looks kind of like a line in different colors. So you can see what happens. And of course, kind of as you'd expect, perhaps, or as is reassured to us also by the fact that we know there are no local minima, these are all ending up in the same spot. Okay, they're all converging to the same thing. You've already seen this picture as well. This is gradient descent run on a non-convex problem in 2 dimensions. And we can see that where we start affects where we end up, right? And it could be that the global minimum is achieved out here, but it could be that actually right here is stationary, which means that there's 0 derivative of the criterion. And so we would run it to here, and then we'd stop. Or rather, it looks like it's here. they're all, sorry, this is a starting point. All these paths are converging here. So that's probably a stationary point. And gradient descent wouldn't move at that point because the gradient's 0. Okay, so for non-convex problems, as we kind of have already been seeing and talking about, we can't expect to get something globally optimal out of gradient descent. So let's go through an interpretation for what gradient descent's doing. It's actually going to be quite helpful for some of the modifications we'll make in future lectures, but it's also just helpful to see, I think. So one way to motivate gradient descent is to consider a second order expansion of my function, okay, about a point x. So let's suppose I'm at x and I'm asking what should I do next. I have an algorithm. I'm going to see where should I move after I've been at x. So now I'll think about essentially expanding the function at a new point y as a quadratic function around x, where I was. And this should look like a Taylor expansion to you, right? F of x plus the gradient of f of x transpose y minus x. But this part is different. Usually we'd see something like y minus, or 1/2 y minus x transpose the Hessian transpose y minus x. That would be a second order Taylor expansion. For gradient descent, I'm effectively replacing that term by this simpler term, which is just the norm of y minus x squared times 1 over 2t. So in other words, I'm replacing the curvature that I know is given by the Hessian by a much simpler notion of curvature, which is just something spherical. It's 1 over t times the identity matrix. So I'm throwing away curvature information. But it's a simpler quadratic approximation. And you can actually show that if I minimize this thing over y, which would be a good practice for you, just to kind of continue to remove the rust from your multivariate differentiation skills, take a derivative here with respect to y, take a gradient with respect to y, set it equal to 0. This thing is just a convex quadratic, so we know we can minimize it by doing that. We're going to get that y is equal to x minus t times the gradient of f of x. So in other words, gradient descent actually chooses the next point to minimize this over all y. Okay, and that's what we said down here. The next point is actually y equals x plus. And if we were to compute what that is, to minimize this, we'd get exactly the gradient descent update. X minus t times the gradient of f of x. Okay, so we can think about this as a quadratic approximation. As I just said, we can think about it also as a sum of two terms. We have a kind of a linear approximation to the function. It's very simple, and a proximity term to x. So this is saying don't go too far away from x. Of course, if we just tried to minimize a linear approximation to our function, that wouldn't be very useful. We'd send y off to infinity in some direction. So this is going to keep us close to x, and it has weight 1 over 2t. So if t is very small, this has very high weight, and we're going to stay very close to x. And you can see that because the gradient update is going to be making a very small multiple of the gradient. And if t is large, then this term has low weight, and we're moving farther away from x. Just some interpretation. Okay, and this is the picture of that. So here, let's say, is my function in dotted line. Let's say blue is x. I'm making some quadratic approximation. That's this thing right here as a solid line. Actually, I'm sorry, I completely reversed the roles of the two curves here. This was my this is the original function, this black. This dotted line is my quadratic approximation. Okay? Let's say blue is the point x, so I'm making a quadratic approximation. This red is what I get by minimizing the quadratic approximation, and that's where I'll go next. So I'll move from here to here. And then I'll go down here on the function, I'll make another quadratic approximation. I'll minimize that, it'll put me out somewhere here. Okay? So that's just a pictorial representation of this interpretation. Okay, so here's what we're going to talk about today. I'm going to try to get through all of it, but if we don't, then we'll either decide to skip gradient boosting entirely, or we will, because it's something that I think is interesting, but it's kind of more purely machine learning, or we'll just do it next time. We'll make that decision. So let's talk about how to choose the step sizes, which is obviously an important aspect of gradient descent. And we're just going to go through it like three examples essentially. So of choices of a fixed step size. So the simplest strategy is to take the step sizes to be fixed. So I just choose t to be these tks that you saw here to be a constant equal to t for all iterations k. And what happens if t is too large? Well, gradient descent can diverge. So that's what you're seeing in this picture. Here I have I have a two-dimensional function, and instead of drawing a 3D plot, I've actually drawn a contour plot. So you can see that these are the contours of my function as a function of, let's say, x1 and x2. The minimum's at 0, 0. I'm starting out here. In fact, it's just a quadratic. This is my function right here. And I'm running gradient descent. And I have a large step size here, in fact, too large. And you can see that I actually start diverging. So I'm moving farther and farther away from the minimum. And at some point, the algorithm's just going to be pushing me out arbitrarily far. Yeah?
On the previous slide, what is the point of the quadratic interpretation?
This thing?
Why do you want the quadratic interpretation? What's the point?
Well, yeah, I'd say so. First of all, we'll actually do something kind of similar in this expansion when we prove a rate for gradient descent. But I would say more helpful is the fact that this quadratic approximation, the same idea, can be used to motivate other algorithms that are maybe less obvious intuitively. So when we talk about proximal gradient in a couple lectures, we'll derive its update by doing something similar. And jumping ahead to Newton's method, in fact, Newton's method is doing this, but using the Hessian itself. So it's a way to connect algorithms or to motivate new algorithms. Other questions? Okay, so yeah, too big step size. I get something that diverges. Of course, if you can kind of guess, if the step size is too small, then it'll be very slow, right? So here is the same example. I've just used a really, really small step size. Here's the iterates. After 100 steps, I'm still quite a far ways from the minimum. Okay, and the gradient itself is getting smaller, right, as I'm getting closer to the minimum. So actually, the effective step is getting smaller as I go on. And if I happen to pick t just right, then here it converges quite nicely. So we're going to actually get an idea of what quite right means, or just right means, when we talk about a convergence analysis, but it has something to do with the curvature of the function. So we'll make that precise in a little bit. Okay, so an alternative, which is, I think, very popular in practice, is just to use adaptive step sizes. So not choose something fixed, but try to guess the right step size at every iteration using some heuristic. And the most popular heuristic is called backtracking line search. There are other ones as well, but this one is, I think, one of the more popular. So let's suppose we're at a given iteration of gradient descent, and we're at x, and we're trying to figure out how big of a step size should we take to go to x plus. So what is the value of t we should use for this update? And let's say we fix two parameters ahead of time, beta and alpha. Beta is something less than 1, alpha is something less than a half. So you fix these typically before you even run the algorithm. So these are just the same at every iteration of the algorithm when you're doing backtracking. So we're going to start with some guess at the step size, something that's relatively large, t init. So maybe something that we think if we were lucky we could take, but otherwise we would have to scale down. And we're going to check the following criterion. If the progress we make by going from x to x minus t grad f, in terms of the criterion, is bigger than where the progress we had, f of x minus this quantity, alpha times t times the norm of the gradient squared, then we're going to actually make t smaller. We'll multiply t by beta times t. So think about beta as, let's say, 0.9 and alpha as a half. So we'll see if we make good enough progress that actually we've decreased the criterion by a half times t times this gradient squared. If we have, we'll stop. If we haven't, if this is actually bigger, then we're going to shrink t. We'll make it 0.9 of what it was. Okay, so we just check this until this condition fails, until we get less than or equal to, then we actually take that update. because we think we've made good enough progress. So it's simple. It tends to work well in practice. It's very popular, and you could think about just taking alpha to be equal to a half. If you want to just reduce it to one parameter, it's also common that you'll see this introduced in textbooks as just keeping alpha equal to a half.
What's the motivation for the square?
Yeah, so that's a good question. I'll give it to you kind of pictorially. So the motivation is actually by thinking about a linear approximation to our function. Okay, if the update direction is delta x. So for us, delta x is going to be minus grad f, right? We're going to be moving from x to x minus t times grad f. But in general, if we actually had an update direction of delta x, the same kind of the same picture would hold. So we're just going to be thinking about this in terms of this generic direction. So we're at, let's say, x, and this is f of x. And so in terms of the gradient update, this is t equals 0, right? If I don't move any distance at all in terms of the negative gradient, then I stay at x, so that's t equals 0. And we take a linear approximation to our function, that's this guy. That's going to be f of x plus t times grad f of x plus delta x. That's comparing, actually. So if I take a linear approximation, let's say f of y around x, it's going to be f of x plus grad f of x transpose y minus x. And if I think about what that looks like at y equals x plus t times delta x, right? At this point I would think about moving to, then this thing is equal to f of x plus t grad f transpose delta x. Okay, so this is the linear approximation as a function of t. By convexity, right? By convexity, we know that it has to lie below the function. That's the property of convexity. That's the first order condition for convexity. Tangent line lies below the function. So we could never hope to achieve this, right? By moving to x minus t grad f, because it's a lower bound in the criterion. So the motivation or the intuition is that we're going to multiply this by some fraction. So we'll degrade the slope a bit by alpha and hope to achieve some fraction of what the linear approximation would give us. So half is like the common choice. So I know I can't do as well as the linear approximation because it's an underestimate, so I'll hope to do as well as half of it. And that's this line, and we're going to try to choose a value of t that puts me at something smaller than this. Okay. So in this example, backtracking, I just set alpha equals beta equals 0.5, and it picked up it picks up the right step size, roughly as a function of iteration, and you can see it puts me at the optimum or close enough in 12 steps. Okay, there are of course more. I'm counting the number of gradient descent steps, the number of times I'm actually performing this. But you can say, well, I'm actually also iterating to check this condition, and so I reported the number of total steps, and that's 40 here. So that's if I count kind of everything combined. And that's similar to what I got with the best choice of fixed step size. Okay, so backtracking and the best choice of fixed step size are going to perform kind of roughly similarly. Our theories can also corroborate that. But with backtracking, of course, we don't have to know anything about what the right step size is a priori. It tries to pick it up every iteration. So I think I'll just mention exact line search and then we'll take a break. So you might say, well, that's a heuristic. I'm going to actually just look at the absolute best I can do along this line segment. So I'll look at all the values of t, or all the values of s, and I'll look at x minus s times the gradient. And this is a one-dimensional minimization problem. I'm trying to make this as small as possible over all s. X is fixed here, right? It's the point at which we're currently at. It's the point that we're at in gradient descent. So if I'm minimizing this over s, it's a one-dimensional optimization. In fact, this is convex. Okay, why is this convex? It's because I'm restricting my function f to a line segment, and we know that any convex function restricted to a line segment is still convex. This is a convex function of s. So in principle, I might think it's a good idea to actually optimize this perfectly and take the very best step size according to this optimization. So it's usually not possible to do this. That's one thing. And a second thing is, if you try to run approximations to, let's say I'm going to run an algorithm now on this, some univariate optimization algorithm. It's typically not as efficient as backtracking, so it's typically more expensive than just checking this condition, and it's also typically not worth it. Doesn't lead to better global convergence. So people don't really do this, except for fairly simple problems. Okay, let's take a break, and then we'll come back and talk about the convergence theory. So let's jump right back into it. I'm going to try to get through optimistically everything before we quit, but I don't know that that'll work. So let's just try. We're going to now state a convergence result for gradient descent that is going to be used, let's say, as a basis for all the comparisons we make in future lectures for different algorithms. So this is the first time you're going to see a rate, but people in optimization care very much about these kind of rates. They describe how quickly an algorithm converges, and we're going to pit this against what we get out of other things as we go forward. So the setting we're going to be thinking about is the one that we've already discussed, convex and differentiable. And I'm going to assume one more thing, which is that actually its derivative is Lipschitz. So this gradient is a Lipschitz mapping, which means that it satisfies the following condition. If I take the gradient at x and I subtract off the gradient at y and look at the norm between these two, then this is less than or equal to L times the norm between x minus y. for any x and y. So there's some constant L that makes this true. I think on your first homework, if I'm not mistaken, you actually proved this, right? This is one of the, I think this is one of the problems we gave you. And this is also equivalent, if f has, let's say, two derivatives, it's equivalent to saying that the largest eigenvalue of the Hessian of f is at most L. It's another equivalent condition. Okay, that was also, unless I'm just forgetting what we had you do, that was also, I think, on your homework. That, you know, L Lipschitz, if you have two derivatives, that is, Lipschitz, is equivalent to the Hessian having the largest eigenvalue at most L for all x. So this is assuming twice differentiable. So the reason I'm saying this is that you can think about the second derivative as reflecting some notion of curvature. Okay, this is a bound on the curvature of our function. So under those conditions, really pretty generic, gradient descent with a fixed step size t that's less than or equal to 1 over L converges at the following, it satisfies actually the following property for all step sizes k, for every step size. The criterion value at step k minus the optimal value is bounded by the square distance between where we started and a solution. So this is any solution, x star. So if there's more than one solution, this statement holds for all solutions. So I could take, for example, the one closest to where I started. It's the best bound. Divided by 2 times t times k. Okay, remember t is the step size here, and it's at most 1 over L. So if I take it equal to 1 over L, which is the biggest step size I'm allowed, you can think about this as like L times this distance, square distance to the optimum, based on where we started, divided by 2 times k. Okay, and in fact, if you use backtracking, the same result holds. Just replace t by beta over L. So again, t equals 1 over L is like the best choice of step size. It's the biggest we can take. And that would look like having an L in the numerator. And if we did backtracking, it would be the same, but with an additional factor of beta in the denominator. Remember, beta is something less than 1, like 0.9. So it just makes the bound a little worse. If we took beta equals 0.9, this is basically the same, just a little worse. Yeah. K is the iteration counter, yeah. So I think almost every time I've taught this, I've actually proved this in class, which is to say that the proof is fairly straightforward. And it just uses properties like, effectively the property you proved in the homework that, you know, having a gradient that's Lipschitz is equivalent to knowing that this is true. I can upper bound my function by a quadratic. Right? So convexity tells me I can lower, this is a lower bound. If I have a Lipschitz gradient, this property is true. That's another thing you did in your homework. This is essentially the jumping point for the proof. This year I decided not to prove it and to prove something actually a little easier in lecture and to put this on your homework. This is the proof on your homework. So it's, you know, we usually have a proof on your homework about convergence of something, you know. I think you guys lucked out because this one is something we did in class in previous lectures, and we're going to structure the homework questions so that you kind of can see all the steps. So we're going to try to prove something else a little bit later. It's actually even easier than this, but uses similar steps so you can get a flavor of the proof. So the way we read this is we say that actually, okay, after k iterations, the gap between where I am and the criterion goes down like 1 over k. Okay, that's how we read it. This stuff does not vary with the iterations. This is just some constant depending on where we started. And so we say it as a convergence rate 1 over k. You write it O of 1 over k. Another way of saying this, and it's going to make more sense to you when we start talking about convergence rates that are not 1 over k, because then this will actually be different. This is going to, when you see these two, they just look like they're expressing the same thing, but changing k for an epsilon. they are actually reflecting equivalent but different notions. So we can talk about convergence rates like this, or we can talk about them in terms of if I were to ask you for an epsilon suboptimal solution, so if I wanted to know this, if I wanted to run my algorithm until this was true for a particular epsilon, so run it until an iteration k for which this was true, how many iterations would I need as a function of epsilon? So this is another way of speaking about convergence. It's actually equivalent to writing it in terms of k, because we can just take the upper bound from gradient descent, right, which is, it's basically just some constant over k. So we know that after k iterations that this is actually upper bounded by this. And so if we set this equal to epsilon, okay, then at least we'll know that after k iterations, we will have an epsilon suboptimal solution. And we solve for epsilon. So if we solve for k as a function of epsilon, we just get c over epsilon. So that's why we say that, let's say, convergence rate was order 1 over epsilon. So I said this is going to seem like it's not as transparent to you because it's of this particular rate. Let me give another example. Let's suppose the convergence rate was order 1 over k squared. Okay, then equivalently, right, I could say, well, that means the upper bound looks like ck squared. And if I want to get an epsilon suboptimal solution, I can set that equal to epsilon. And I'll see that actually, by solving for the number of iterations I need, it'll be something like this. So in terms of epsilon, that's the convergence rate. Okay, so we can talk about them both ways, as a function of k or as a function of epsilon. So I'm going to now give you a few more results, and then we're going to prove actually one of these results, the last one that we come to. So this was for gradient descent under this condition, which is really quite generic, with fixed step size or backtracking, order 1 over epsilon iterations. You could ask, what happens if I actually know more about the function? So I know that it's strongly convex, as well as having a Lipschitz gradient. So Lipschitz gradient means that I can upper bound the function by a quadratic. Strong convexity, again, this is something you proved in your homework, means you can lower bound the function by a quadratic, by a quadratic where I place L by another positive constant m, if m is a strong convexity constant. Okay, that's in the case when I let's say I have a smooth function. So Lipschitz and Lipschitz gradient and strong convexity together means that I can sandwich my function between two quadratics. So you have a very precise understanding of its curvature. Can't be more curved than L, can't be less curved than M. And in that case, you can actually say a lot more about how fast gradient descent converges. And we get a very different looking result. Okay, and it's important to point out the difference. So in that case, we can say that actually, if we take step sizes that are a little smaller, okay, less than or equal to 2 over m plus L, then the progress after k iterations looks like some positive constant, c. C is actually strictly less than 1 to the power of k, times the Lipschitz constant over 2 times the distance to where we started, square distance to where we started to the optimal. So as a function of k, this actually looks like c to the k, where c is something less than 1, which goes to 0 a lot faster than 1 over k. Right? It's a very different nature of convergence. And so if we write this in terms of how many iterations does it take to find an epsilon suboptimal point, again, just repeating this calculation one last time, right? If I have this as my convergence rate, then I can say, well, setting this equal to epsilon and solving for epsilon, I get that it's on the order of 1 over epsilon iterations times a constant. So I think this is the maybe more natural way to think about the comparison. So let's think about gradient descent. Let's say in the case when I know that I have a Lipschitz gradient, or in the case when I additionally know that the function is strongly convex. Okay, 1 over epsilon and log 1 over epsilon are extremely different. Right? This guy is going to be much, much, much smaller. Take epsilon, to be 2 to the minus 10 or something like that. That's probably really small, 2 to the minus 6. Okay, and let's say this is log base 2. That's the difference between 6 iterations and 2 to the 6 iterations. So if I'm trying to converge to a very, very accurate point, so if I want to get a really kind of small epsilon guarantee, then this is a much faster convergence regime. So people in optimization, oddly enough, call this linear convergence, even though it looks exponential. But this is something that we're going to adhere to. And they do it for kind of a silly reason, but it is the reason. If you were to plot this on a plot where the y-axis is on a log scale, then it looks like it goes down linearly. That is actually the reason. So we typically do that. And you can see that here's an example I took from the Boy and Vandenberg book. K is the number of iterations. And this is the distance, or this is the difference between the criterion at iteration K and the optimal one. It's on a log scale, and so it looks like it's converging linearly here at this rate, some c to the k for c less than 1. So a very important thing to point out about gradient descent is that this contraction factor c, so this thing that determines the rate, it actually depends on the condition number of my function. So it depends on the ratio of the largest eigenvalue to the smallest eigenvalue of its Hessian. And that's actually upper bounded by L over M. Okay, because this is the largest eigenvalue is upper bounded by L. The smallest eigenvalue is actually lower bounded by M under M strong convexity. So we can think about L over M as at least an upper bound on the condition number. Or if we just took L to be the largest eigenvalue and M to be the smallest eigenvalue, it's exactly the condition number. And the higher this condition number, the slower the rate, because this contraction factor c is actually going to get very, very close to 1. So as this L over M gets large, this contraction factor c approaches 1. And so it actually affects our convergence drastically. So this is not only affecting this result. If I were to write this out for you in terms of its dependence on L and M, you'd see it. It's also something that's very apparent in practice. If we have functions that are very poorly conditioned, so which means that they are very curved in some directions and not very curved in others, then gradient descent does very poorly. This bound actually describes, even though it's an upper bound, it describes pretty realistically what happens in practice. So it's an important fact about gradient descent that we're going to, see that second order methods, for example, remedy this. Yeah.
In really high-dimensional settings, you have some sparsity in terms of maximum curvature in certain directions. Do you get better convergence, or is there sort of optimization you do to improve that?
That's a good question. So I'll paraphrase it by saying, if you're in high dimensions, but you know that you're in some locally favorable region, do you get better convergence? And the answer is yes. People have papers that prove that, even if functions, let's say, aren't globally strongly convex, if they're strongly convex in a neighborhood around the optimum, then you'll get a locally linear convergence rate. And so if you're close enough, things will converge very quickly. These kind of things typically require just more assumptions. But yeah, this kind of worst case analysis, a global analysis as well, is not always telling the full story. Other questions? All right, so we're going to do a few things. Looking at the conditions, first of all, I just wanted to give you a flavor of what this means for your probably favorite / most familiar problem, which is least squares regression. So if I just was minimizing this function with gradient descent, which probably wouldn't do, but we could think about it at least. What would gradient descent do to this function? So what does it mean, first of all, to assume Lipschitz continuity of the gradient? Okay, what is the gradient of this function? Somebody should yell it out for me. I'll even put a half in front, let's say, to be nice to you guys. Gradient What's the Hessian? That one's probably easier. Is it on the slide? It is on the slide. So you guys should, I'm thinking everyone's just being shy. You guys should really know the gradient of this function. You guys should get a tattoo if you can't remember it at the end of the course. It's just this. It's just the chain rule. That's the gradient. Equals that thing. And the Hessian, let's say, is equal to x transpose x. Okay. So what does it mean, for example, to assume a Lipschitz continuity of the gradient? Well, remember we said that's actually equivalent to saying that the Hessian has largest eigenvalue bounded by L. And since the Hessian is x transpose x, it's actually a constant, doesn't depend on beta at all. Then this condition is met by taking, let's say, L to be the largest eigenvalue of x transpose x. Or here I'm writing the largest singular value of x squared. So in order to know what the optimal step size is, we'd have to actually compute this. That would be a horrible idea if x was big. So it's probably better to use backtracking, right, in this problem. If we were running gradient descent, that is. Unless we somehow knew what this was. But it's not unrealistic to assume that this is true. Of course, it's true just by taking this for L. So certainly this condition is reasonable for this particular function. How about strong convexity? Well, that means that the smallest eigenvalue is lower bounded by m of the Hessian. The Hessian, again, is x transpose x. So that's true, let's say, if I took m to be the smallest eigenvalue of x transpose x. Or here I'm writing the smallest singular value of x squared. Same thing. Well, we can immediately see that if x is wide, so if I'm in the high dimensional case where, let's say, I have x being n by p, where p is bigger than n, so in this regression context I have more features and observations, then x transpose x is singular. Its smallest eigenvalue, let's say, is 0, or the smallest singular value of x is 0. So it's not strongly convex. And I don't get that locally, I don't get that linear convergence rate. And even if it happens to be strongly convex, then we can see that the condition number here can be very large. So if I have features that are very correlated, then the ratio of the largest singular value of x to the smallest singular value of x squared, which is the condition number, could be very large. So even in the strongly convex case, which is to say we're in a low dimensional case, you know, this can be very large, and so that contraction factor C can be very close to 1. Just giving you some intuition for the conditions by looking at a simple case. Let me go through this quickly, because I'm going to try to, in the last 12 minutes, state a result for non-convex problems and prove it, which is actually simpler than the proof for convex problems. And then we won't get to gradient boosting, but we'll decide whether to cover that next time. So some practicalities and pros and cons. So stopping rule typically is stop when the gradient is small. That's the stopping rule we typically use in practice, because the gradients, of course, is 0 at a solution. And one thing you can show is that if f happens to be strongly convex with a parameter m, then the gradient being smaller than this number, square root 2m times epsilon, implies that we are epsilon suboptimal. So if we happen to know the strong convexity parameter, then this rule would guarantee us epsilon suboptimality. We'll learn much more about stopping rules when we learn about duality and how to bound the duality gap. But for now, we can just say stop when the gradient is small in norm. Pros and cons, I think we went over some of these. It's simple. Each iteration is typically cheap, right? You're just computing the gradient, and you're just moving in that direction. So there's no matrix multiplication required to at least compute the update if the gradient is known. Or there's no linear system that's being required to solve to compute the update. It's just adding two vectors, x and the gradient. So it can be fast for well-conditioned strongly convex problems, as we saw, but it can often be slow because many interesting problems aren't strongly convex or they're poorly conditioned. So that's one of its cons. And another con that's a major one is that we can't handle non-differentiable functions. If I gave you a convex function that didn't have a derivative, so far we don't know what to do, okay, because everything's based on computing the gradient. So we'll see how to remedy kind of these cons either by extending gradient descent or by moving to second order methods. We'll kind of revisit these throughout the semester. So one quick comment. You might say, well, Okay, that's great. You presented a rate of 1 over epsilon for gradient descent. Is that optimal? Can you actually do better, or is gradient descent achieving the optimal behavior for first-order methods? So it makes sense to restrict ourselves to first-order methods because we're trying to be thinking about if all we knew was how to access the gradient, is gradient descent the best we can do? Or is there some other method based on gradients alone that could do better? And first-order methods are actually precisely defined as follows. It's an iterative method which updates, let's say, the kth point somewhere in the span of all the gradients seen so far plus the initial point. And you can prove that gradient descent actually is one of these methods by induction. So if you use induction, you'll see that at the kth iteration, the gradient update is actually in this set. So anything that satisfies that is called a first-order method. So there's a very important theorem by Nesterov in the early 80s. Nesterov is a giant in optimization. We'll actually refer to him lots in this class. That shows that there's a lower bound on how well first-order methods can do in terms of their convergence. For the functions that meet the same assumptions as those that we put down for our rate, Lipschitz gradient. And that lower bound, actually, for any first-order method, depends on k squared. So you look at our upper bound, which depends on k. This lower bound depends on k squared. And now one of two things happens. Either Nesterov was loose, so he could have done a better job, which wasn't the case, by the way. It's very rarely that'll be the case. Or gradient descent is suboptimal. So there's some other method that actually achieves this lower bound, some other method that converges faster. And the answer is actually the latter. There is another method that converges faster, and it's called accelerated gradient descent. And it's also attributed to Nesterov. So we'll talk about that in a few lectures. That we can uniformly improve on the convergence rate of gradient descent using a technique called acceleration. So I think I'll only have time to state the result and maybe even start the proof for non-convex functions. So this is the last thing I want to say. What can we say about non-convex functions? So it turns out for non-convex functions, we can say something very precise, and the proof is pretty easy, under the same assumptions, but without convexity. So it's smooth and has a Lipschitz gradient. What is gradient descent going to do? Well, asking for optimality is too much. We know that we can't necessarily converge in general. We've seen pictures that already demonstrate that. So we're going to settle for what's called epsilon stationarity, which means that we're going to try to find a point whose gradient in norm is less than or equal to epsilon. If that's true, then we have what we call a stationary point. Okay, at least we're making the gradient small. And the result is as follows. If we take the step size to be less than or equal to the familiar 1 over L, then after k steps of gradient descent, the smallest gradient we've seen so far in norm, okay, because this thing actually need not be monotone, the smallest gradient we've seen so far is bounded by twice times, this is supposed to be 2 times the quantity, the criterion gap where we started, divided by the step size times k, square root of that whole thing. So it means that if in terms of epsilon stationarity, it takes us 1 over epsilon squared iterations to find an epsilon stationary point for any non-convex function that's smooth and has a Lipschitz gradient. Very interestingly, compared to the last slide, this rate can't be improved. So gradient descent on the bigger class of non-convex functions with Lipschitz gradients is actually optimal. You cannot improve on this. That's not only true for first-order methods. For any deterministic method, there is no method that uniformly improves over this rate. So this is the best we can hope to do. And you might think this kind of fundamental result was also done a while ago. It's actually done last year. So this is a very nice paper that was written last year, posted on arXiv, talking about lower bounds for finding stationarity points. So lower bounds for non-convex problems are a topic of interest that are kind of currently being developed. So I think this is a pretty fascinating result. Yeah.
The value of the function that we see.
I'm sorry, I don't understand the question.
Is it the local optimum or the
This here? This is the global optimum. Yeah. This is the global optimum of the function. But it's a criterion value, right? So think about it, this is some constant. So we're currently interested in how this goes down with k, let's say. Okay, 5 minutes. I think that's enough. We'll see. The proof is actually quite easy. It's on that slide. And I wish I didn't have to write down the first line because I already wrote it down for you. But the first line of the proof is, and maybe I'll just kind of jam through this, and then next time I will discuss proof strategies at a more high level to give you some intuition. So by Lipschitzness of the gradient, okay, suppose we're at a point x, and we're going to make the next update. We know this is true for any y. So if we plug in the gradient update, okay, then we'll see that actually f of x plus, that's the, let's say we'll call that x plus, that's the next iterate, is less than or equal to f of x plus, actually going to be minus t times grad f of x transpose x plus, this is going to be, I'm sorry, this is going to be the gradient squared, right? Because I have y minus x is going to be minus t times the gradient transpose itself, so I get minus t times the norm of the gradient squared. Here I'm going to get LT squared over 2 times the norm of the gradient squared. Just plugging in for this update. Okay, so in other words, this is going to be equal to f of x minus t times 1 minus LT over 2 times the norm of the gradient squared. Okay, so when t is, let's just call this thing w. Okay, and when t is, if I take t to be less than or equal to 1 over L, w is going to be positive. So I could rearrange this statement. So here I have the criterion at the next iteration is less than or equal to the criterion where it was now, minus something positive times the norm of the gradient squared. Okay, just rearrange that to say that the norm of the gradient squared by moving this to the other side, moving this to the other side, is less than or equal to, you know, whatever this positive constant was, 1 over w times f of x minus f of x plus. So we've tracked how small the gradient is getting, essentially, as a function of the criterion gap between this iteration and the next. Now, we're basically done. Just add up this bound. Over, let's say, all iterations I, starting from the very, let's say 0th initial one to k. So think about now putting an xi in here, and this becomes xi plus 1. Okay, this is going to be less than or equal to, what's going to happen here is we get a telescoping sum, right? Essentially, every term that appears in for one I, it appears at the negative for the next I, except for the first and the last, which don't cancel. Okay, that's the result of just adding up this over all the iterations. And we're going to bound this by 1 over w times f of x0 minus f star, right? Because that's surely smaller. It's the optimum. And this thing, okay, this thing is going to be bigger than or equal to itself, let's say k plus 1, times the minimum of all the gradients squared. Right, because I'm adding up all the gradients. If I took the smallest one, it's going to be, this is going to be bigger than or equal to the number of terms in the sum times the smallest. And so I have now this bound. This is less than or equal to this, and that is our result. That's all it is. The smallest gradient we've seen so far. Now say squared is less than or equal to this particular criterion gap divided by k plus 1. Taking a square root is this gives you the statement on the slide. Okay, so I think I did it just in time. That was pretty fast. Next time I'll give you more of a high-level kind of overview of the structure. And the proof on the homework, by the way, that you'll see next homework is actually quite similar to this. It's just surprisingly a little more difficult for convex functions. I will see you guys, is today Wednesday? I'll see you on Monday. Don't forget to turn your homework.